very fast, just to recap what we are here. To conjugates full molecules to the xenobiotic. Phase 1 reactions can be oxidation reactions. Those are very important, carried out by cytochromes P450. Phase 1 reaction can include epoxidation. This is epoxide is a very reactive compound, so they can be bioactivation reaction, toxifying non-toxic compounds. Of course, oxidation reaction can also happen not only on carbons, but also on other elements. Dehydrogenation. So it is dehydrogenation is a synonym of oxidation. So alcohols can be oxidized to aldehydes, and aldehydes can be oxidized to acids, carboxylic acids. Also, reduction site mechanism of dehydrogenation or oxidation. Hydrolysis, dealkylation. Usually dealkylation is oxidative, so it is carried out at a non-carbon atom here, and we obtain the corresponding non-carbon atom containing molecule and the oxidized form of the remaining part of the molecule. Different kinds of halogen removal, again with oxidation often. And then phase 2 reaction, we can observe, let's say, 3 major kinds of phase 2 reaction. Glucuronide conjugation. Glucuronide is this molecule similar to glucose, but with carboxylic acid function instead of an alcoholic function. Glutathione is this molecule, is a tripeptide, so 3 amino acids together. And sulfate conjugation. So in this case, we add a sulfate group, which is of course permanently charged, so the molecule becomes much more hydrophilic. And also methane, in this case, the molecule becomes more lipophilic. Okay, so in this case, it can be, let's say, more dangerous, the molecule, or less easily excreted, less easily eliminated by the body. Okay, then we have seen some, say, recap of redox reactions, but this is, let's say, not so important to have it at hand if you need it when you study our started with the single elements, toxic properties of single elements. Sorry, this is, of course, it's not hydrogen, it's lithium. We have seen lithium toxicity, and then heavy metal toxicity, in particular those 5 elements that are considered heavy metal, even if arsenic is not truly a metal. So we have seen that heavy metals have a common mechanism of toxicity, which is the reaction with electron-rich groups, particularly in proteins, because those ions are electron-poor, so they react quite easily with electron-rich structures in proteins. So thiol group, amino group, and carboxylic acid groups. And then the single elements of the most important single elements of heavy metals, starting from chromium and mercury. You've seen some example of mercury toxicity. Lead, also with some information on heavy metal detoxification, the so-called chelation therapy. Of course, chelation therapy can also be used not only as an antidote in case of poisoning for humans and animals, but it can also be used for detoxification of polluted soil, for example, okay, just by adding this kind of compounds to water and washing in some way, okay, soil or any other contaminated part of the environment, okay. Of course, in this case, the heavy metal becomes water soluble, since we have seen that the purpose of those chelating agents is to bind the metal and make it much more hydrophilic. So water can dissolve it, and we can, let's say, wash down the heavy metal, also in the environment. And arsenic. You've seen that it decouples the production of ATP from cellular respiration. So in respiration doesn't produce any more ATP and the cell dies. Again, the same kind of detoxifying agent can be used, of course, for arsenic too. So this was last time. Okay, I hope everything clear about those compounds. And this is the last heavy metal we will see, which is cadmium. Cadmium is used. Cadmium can exist apart from the metallic form as cadmium 2+. Cadmium, it was still sometimes used for rechargeable batteries. Nowadays, it's almost totally substituted, replaced by lithium-ion batteries, but we still find some nickel-cadmium batteries. It was used in pigments, dyes, for example, the famous orange dyes used by Van Gogh were cadmium-based pigments. And the same, let's say, kind of compounds, in particular cadmium sulfide and cadmium selenide, are used to color plastics. Of course, this is being phased out, gradually abandoned, but still used in some ways. Okay, and some scientists think that the mental health problems of Van Gogh could be, at least in part, due to the fact that he used a lot of those yellow and orange pigments containing cadmium. As you can see, let's say that the life of painters was quite dangerous, because we've seen lead and arsenic-based dyes or pigments, and also now cadmium dyes. Of course, all of these are being eliminated, and nowadays painters are, let's say, less endangered. In the environment, we can find cadmium due to its occurring in minerals to together with zinc, lead, and copper. So when those metals are smelted from minerals, a lot of cadmium is washed out with the minerals. Of course, it should be, let's say, eliminated in a correct way, but it can be in some even small amounts can be eliminated in the environment. Okay, so it can happen. It can happen that it is eliminated in the environment. Coal burning is a source of cadmium. Cadmium is an important impurity of coal. So when you burn it to produce energy and heat and so on, of course, some amount of cadmium will go into the atmosphere if we don't have sufficient purification systems for exhaust fumes. And for the same reason, the incineration of waste containing cadmium, of course, will produce air pollution, cadmium air pollution. So we have seen that it is used for plastics, and so if we burn plastics, we also let cadmium go into the environment. Probably the most important form of cadmium exposition is through ingestion of contaminated food, but the second one is surely cigarette smoke. As we have seen with arsenic, also cadmium is an important contaminant of tobacco. So when we smoke cigarette or tobacco in general, we also intake some amounts of cadmium. And you may imagine that if you smoke, of course, every day, you intake some cadmium dose together with arsenic and so on. Okay, so this is a classic chronic toxicity. And also, just like for mercury, we find high levels, we can find high levels of cadmium in seafood, since seafood are, let's say, filtering water in order to feed themselves. And so by filtering a lot of water, if there's even small amounts of cadmium in the water, of course, these seafood will intake a lot of, let's say, a big dose, since they filter so much water every day. And also organ meats. So when you eat meat, let's say lung, heart, and guts of animals, it can contain, it concentrates, those organs concentrate cadmium. So you can intake an higher amount of cadmium by eating, let's say, other kinds of foods, and in particular other kinds of meat. Okay, so muscle is less concentrated in cadmium. Okay. Okay, of course, cadmium is also acutely toxic, so lethal dose is about 1 gram, but toxicity of cadmium is chronic toxicity, so very small doses for long times. The body possesses detoxification systems for cadmium, so there's a specific protein that can bind cadmium and eliminate with the urine. But of course, it can be sufficient only if the cadmium dose is very small and the exposition is not too prolonged into time. One of the most important target organs of cadmium is kidney, and of course the consequence is renal insufficiency, and in addition to kidneys, also the liver is the other important storage organ. And of course, you will find that the liver is also damaged by cadmium. And this, of course, just I have seen before, explains why by eating organ meats we are exposed to higher doses of cadmium. But cadmium is also, again, just like we have seen for lead, for example, similar to calcium. It is an ion, so it can be incorporated into bones, and of course this means that bones don't have the usual mechanical strength. Okay, so also bone damage can incur. Okay, and finally, it is also carcinogenic. So chronic exposure can produce cancer. Okay, and the final element we will see as a toxic element is not an heavy metal, is a non-metal. Let's say that is one of the most important elements in our body, but even this can be dangerous. And there's a lot of talk nowadays about oxygen. Of course, oxygen, we have seen it's essential to life, in particular for cellular respiration. However, just like anything, you may remember that it is dose that makes the poison. It can have toxic effects, but oxygen can have toxic effects even at normal doses we find in the normal atmosphere, in the normal levels we have in our bodies. Why? Exactly due to the fact that it is involved into the cellular respiration mechanism. In particular, you see here, we have already seen it before, that oxygen is reduced to water, okay? Also to carbon dioxide. But what is interesting for us is the reduction mechanism to water. This mechanism can be seen as a multi-step pathway. You may remember that this process, oxygen being reduced to water, happens during the electron chain, which is the final step, the third and final step of cellular respiration. So, in this step, where the energy is stored in ATP, we have the reduction of oxygen molecules to water, and oxygen gains 2 electrons, and as a consequence also 2 hydrogen ions to produce, in fact, water. Okay, so this can be seen as a stepwise process where oxygen initially receives 1 electron, so 1 electron at a time. And as we know, when we take a molecule or an atom and we give it a single electron, we produce a free radical. And free radicals are, in fact, very reactive, since this is a stable molecule. So if we add an electron, this is no more stable. It is stable no more, okay? So it will be very, very reactive. It tends to react very easily with anything that it encounters in the cell. So you may imagine that this happens every day, continually, when we have cellular respiration. This is called superoxide ion, and it is a free radical, in fact, okay? Then the superoxide radical reacts with 1 hydrogen ion to produce another radical. Here, we don't, let's say, we don't change the fact that this is a radical. So even the product is a radical too, and it is called hydroperoxy radical. Again, very reactive. And then we can have the second electron addition to produce hydrogen peroxide. Hydrogen peroxide is not a radical, but it is still very reactive. In fact, we have specific enzymes in our body called catalases used to detoxify this compound, hydrogen peroxide. And one of the important toxic reaction that hydrogen peroxide can undergo in the body is the reaction with iron ions. You may remember that iron ions are contained in the cytochromes, and cytochromes are exactly the enzymes that carry out the last electron phase of cellular respiration. So there's a lot of iron near when we have creation of hydrogen peroxide, and this can lead to the formation of the hydroxyl radical. Again, another radical, very, very reactive. So you see that during the electron chain phase of cellular respiration, a lot of radicals are formed, and all of them are very reactive. In particular, this one, while the previous radicals are very reactive, but let's say that they are physiological, okay? So it is normal that they are produced, and the body has some detoxifying systems in order to avoid most toxicity due from those radicals. In this case, this reaction, the so-called Fenton reaction, from the name of the chemist who described it for the first time, this reaction is, let's say, not physiological. So the production of hydroxyl radicals can be dangerous. It can attack many proteins and DNA, either directly as such, or by reacting with some other compounds and producing other radicals. So this is you may have heard that a lot of food supplements and nutraceuticals are used nowadays in order to avoid oxidative stress. It seems that oxidative stress is one of the most important, or an important contributing factor to aging. And when we talk about oxidative stress, we are talking about all of these reactions that produce free oxygen, or the so-called ROS, reactive oxygen species. Okay, so this is the reason why many food supplements are being sold against oxidative stress. Another toxic form of oxygen is ozone. Ozone is present in let's say, two parts of the atmosphere. In the upper part of the atmosphere, which is called stratosphere, it is naturally produced by the action of UV light. So UV light, of course, is part of the light of the sunlight. Okay, and so every day our stratosphere is impacted by sunlight and thus by UV light. And UV light produces in fact, with its high energy, produces ozone from oxygen, okay? Because part of oxygen molecules are directly broken down into oxygen atoms, single oxygen atoms. Those are also radicals, and they produce one oxygen atoms plus one oxygen molecule produces ozone. This is a, let's say, natural reaction, and the ozone layer in the atmosphere is UV opaque. It means it doesn't let most UV rays pass, so it protects us from UV rays. So ozone in the atmosphere is natural and it is beneficial to life on Earth. Okay? It protects us from damaging UV rays. However, the other part of atmosphere where ozone can be produced is in the lower part of the atmosphere where we live. Okay, so immediately over the Earth crust. And usually this ozone is not naturally present in high concentrations, but it is produced due to air pollution. In particular, nitrogen oxides are very easily broken down by UV rays to produce other less oxidized nitrogen oxides and oxygen atoms. And as we have seen for the stratosphere production of ozone, oxygen atoms react very fast with oxygen to produce ozone. And since nitrogen oxides are among the most important products of hydrocarbon burning, of course, nitrogen oxide are very frequently present in the air, in cities, and wherever heating systems for homes and cars are present. Okay, so hydrocarbon burning produces nitrogen oxides, and nitrogen oxides through the action of UV light produce oxygen atoms that react with oxygen to produce ozone. And ozone in the lower part of the atmosphere is dangerous because ozone is an oxidizer and it can react with metals to produce oxides. And this is, of course, not let's say, not a good thing, but even worse, ozone can react with organic molecules, and in particular with alkenes. Okay, so molecules contain double bonds, and ozone will break down the molecules, so it will degrade a lot of organic compounds. Almost all organic compounds in our body contain at least one double bond, okay, producing very different molecules, oxidized ketones or aldehydes, okay. And so it can be very, very toxic, in particular, a very strong irritant, of course, according to the concentration in air. And since ozone is a gas, of course, the most important form of toxicity is, but it is a gas, it is also immediately brought to the alveoli and from there to the blood. So it can have an irritating and toxic activity also on cardiovascular and central nervous system. In particular, for the respiratory system, we have asthma, bronchitis, and if you expose to low ozone doses with air pollution, like in cities, we have a big increase in the incidence of asthma and bronchitis in people living in cities, in part due to this effect. Of course, this will increase your chances of dying from respiratory illness in a chronic way. But the main mechanism is inflammation. So ozone in the upper atmosphere is protective toward UV radiation, but in the lower part of the atmosphere is an important pollutant for humans and for the environment. Okay, so this is all for let's say the most important toxic elements. If you take a look at the virtual web page for the course, you will find that there's also another file regarding the toxic elements. It is, I think, called Other Toxic Elements, and there you can find some very brief information on, of course, other toxic elements. We will not see them right now in the lessons, and they will not be included into the exam questions. Okay, you don't need to study that part of the slides, that file, that presentation. It is just for your information. If you are curious, let's say, or if you want to have more information on other elements and their toxicity, you can take a look at that. It's just, let's say, more information for you, nothing to be studied. Okay, now we have started with elements, which are, of course, the simplest form of chemical compounds. Now we go one step up in complexity, talking about inorganic compounds. So it is matter made from more than one element. In particular, we will see the toxicity of a few gaseous and a few, just two, in fact, solid inorganic compounds. Let's say that they could be probably the most important toxic inorganic compounds. So, starting from gases, the first one is carbon monoxide. Its formula is CO. And we have a double bond here between carbon and oxygen. The major source of carbon monoxide is the incomplete combustion of carbon-containing fuel. So we know that when we burn hydrocarbons, and in general carbon-containing fuel, the most important products are water and the carbon dioxide. But of course, some other compounds will form through sulfur oxides and so on and so forth. But carbon monoxide is a peculiar kind of byproduct, since it is, of course, it is present very small amount in normal, let's say, combustion of fuel, but it is produced in high amounts when combustion is incomplete. So when oxygen is not concentrated enough. Okay, so when we have a small amount of oxygen and we burn some hydrocarbons or some organic fuel, we will produce a lot of carbon monoxide. In fact, of course, it is, let's say, it is like carbon dioxide, but with less oxygen. Okay, so carbon dioxide is CO2. Okay, so if you have, let's say, half the oxygen, you will produce carbon monoxide. Okay. Carbon monoxide is very dangerous because it can bind very strongly to hemoglobin and oxygen to all body tissues. And it is about 200 times more strongly attracted to carbon monoxide than to oxygen. So in the presence of even small amounts of carbon monoxide, all carbon monoxide will get bound to hemoglobin and it will displace all oxygen. So you may imagine that if you have hemoglobin not carrying oxygen, all tissues will be damaged. And in particular, the first organ to be damaged is the brain, since it doesn't have any oxygen reserves, and it totally depends on blood bringing oxygen to it. Okay, so according to the different concentration, we can have, let's say, some mild symptoms like dizziness, headache. In particular, headache, strong headache, is one of the most important warning signs of carbon monoxide poisoning and awareness. And if the concentration becomes higher, we can lose consciousness. And of course, at this moment, if there's not someone else who can help us, this is practically death, assured death. Okay. In fact, if you lose your consciousness, you will stay where there's carbon monoxide and will receive permanent brain damage up to the death. One of the symptoms of carbon monoxide poisoning can be cherry red skin, but not always. Okay, so say that it's not diagnostical. Okay, you cannot say that this is not carbon monoxide poisoning since we don't have cherry red skin. Okay, it's also carbon monoxide is very dangerous since it is colorless. It is a gas, colorless and odorless. Okay, so you will never perceive anything, even if you are being poisoned with the carbon monoxide. This kind of poisoning, unfortunately, happens relatively frequently with heating sources in homes. Okay, if you don't have completely sealed heating systems, if your heating takes oxygen from the internal part of the home, it will consume oxygen, and at some time it will start producing carbon monoxide, since you don't have any oxygen anymore to produce carbon dioxide. Carbon dioxide is not particularly toxic, so when you start producing carbon monoxide instead, it is very dangerous. Many cases of this kind of poisoning are reported every year in almost all over the world due to malfunctioning heating systems, domestic heating system. So nowadays, all heating systems are sealed outside the home. They take oxygen only from the outside. But of course, old systems and some kinds of malfunctioning where the system is not completely sealed or the sealing is malfunctioning, they can cause poisons. So always maintain very, very well your heating system at home. Okay, so this is all for carbon monoxide. We can stop since it's already 10 o'clock, and if there's any question, please write it down. Otherwise, we can take a break and see you in 15 minutes. Oh, I think I forgot. I forgot to start recording. Sorry. Please remind me. You know that I tend to forget it. Okay. Sorry. Please remind me when we start after the break. Okay. Thank you. Yeah. So they should already be on Virtuale. It is the old version, but cadmium and ozone are not there. Okay, they are not there in the new slides, since last time we didn't talk about the cadmium and ozone. but they are in the old slides because I have not deleted them, okay? So if you take the first part of the old slide, they should still be there, I think. If not, I can upload right now the slides, the new ones, of course. Okay, someone is writing something. No? Okay, but I will take a look at Virtuale and see if there's need to upload. Okay, so probably it's my bad. Okay. So I probably forgot the last slides and thought we already did all the topics. So I deleted something that I shouldn't have. I will immediately upload them. Sorry again. Just remind me to start the recording as we come back from the break. Okay. Thank you. Okay, I'm back. Let's start the recording. Okay. And slide sharing. I have uploaded the last part of Toxic Elements to Virtuale. You should see it now. And let's see if I can. I will repeat the first hour by myself and upload it also. The link, I mean, to Virtuale. So you will save everything because right now we have lost the first hour of today's lesson. Okay. So if there's no particular question, I will go on with another class of toxic inorganic compounds. And those are oxides, in particular sulfur dioxides and nitrogen oxides. Someone is writing? Okay, I will read after. Those kinds of oxides are treated together since both of them are produced by burning fuels. Nitrogen oxides mainly by car engines, and sulfur dioxide mainly by coal burning, but of course both can be produced by the other source. So we can speak of, in general, of fuel burning, okay? And these are gases, of course. So they exposure is mainly through the lungs, and they are irritants to the lungs, to the respiratory tract, but also to the skin and the eyes. So urban city pollution is known to be very important for this kind of symptoms of these kinds of problems. Okay, and the mechanism of toxicity is, let's say, a bit different than we have seen until now, since they can dissolve into water, and you may know that within our lungs, within our respiratory tract, we have a very thin film of liquid, which is mainly water, and so when these gases come into contact with our liquid film that covers all the alveoli and the bronchi and so on, they will produce strong acids, in particular sulfuric acid from sulfur dioxide and nitric acid from nitrogen oxides. And both of them, those acids are strong acids, and in particular, nitric acid is also an oxidizing agent. So you may imagine that both of them are quite dangerous, and they can be very irritant to the respiratory tract and to the skin and the eyes. For the same reason, when they go into the atmosphere and they go into, let's say, clouds, they can become acids, sulfuric acid and nitric acid, and come down with the rain. Acid rain was very, very important pollution effect during the, let's say, 80 and 90 of last century, and the 80s and 90s of the last century. Then we had the introduction of catalytic exhaust in cars, and of, let's say, methane use for central heating, domestic heating. Methane is particularly, let's say, good for this purpose, since it doesn't contain practically no sulfur and no nitrogen, so it will not produce the corresponding oxide by burning it. And for cars that burn, of course, gasoline containing sulfur and nitrogen, we have used catalytic exhausts. This has much reduced the incidence of acid rain, but not completely eliminated the problem. Hydrogen fluoride, HF is the formula. It's a quite strong acid, and it is a gas. And it is used in large amounts for the fabrication of electronics and semiconductors. So you can imagine all the electronics production, manufacturing industry is using huge amounts of hydrogen fluoride, or hydrofluoric acid. It is a synonym. And for glass etching, but this, let's say that it's a niche use. Only a few people do glass etching, but the same mechanism for glass etching is used for producing and for printing electronics on silicon boards or silica boards. So this is very important nowadays. Again, the mechanism, the main mechanism is that of the acid. So just like any other strong acid, this gas can irritate any exposed area. Of course, mainly, since it's a gas, mainly the respiratory tract area, and also the skin, if it is present in the atmosphere, can come into contact with the skin, and this mainly a curiosity, but the wounds produced by hydrogen fluoride are particularly difficult to heal, so they will stay open a lot of time. This, let's say, a negative side effects of having hydrogen fluoride burns. Very similar to hydrogen chloride, to hydrogen fluoride, hydrogen chloride or hydrochloric acid. Hydrochloric acid is used in the manufacturing of important compounds, since phosphoric acid and ammonium chloride are produced from hydrogen chloride, and both are used to produce fertilizers. And fertilizers are among the most important chemicals all over the world, because agriculture nowadays is practically totally dependent on fertilizer to obtain high yields of crops. Okay, so it is very important industry in all over the world. It is also used in dyes and pigments for paints, as a lab reagent, and as a metal treating agent. It is used to etch metals, just like hydrogen fluoride is used for glass. Of course, toxicity is very similar in its characteristics to that of hydrogen fluoride, since it is a strong acid and is gaseous, but it is less toxic than hydrogen fluoride. So it can cause toxicity to the respiratory, up to death in particularly severe cases. But as I say, this is similar but less severe than hydrogen fluoride. Of course, hydrogen chloride can be dissolved in water. You produce an hydrogen chloride solution, and this solution is again toxic, especially if it is ingested, but also by contact with the skin, for example. Both acids, being strong acids, can cause burns on the skin and on the eyes upon contact. Hydrogen cyanide, and in general cyanides, are still used as insecticides and rodenticides against mouse and rats in homes. Of course, it is poisonous. I think it is the most famous poison all over the world. All the mystery novels and movies always included either arsenic or cyanide poisonings. Okay, the mechanism of toxicity is the binding to iron in the cytochrome C oxidase, which is included into the electron chain, the electron transport system. So again, also cyanides can block cellular respiration. Not only this, but it can also bind to hemoglobin. So it also has a mechanism similar to that of carbon monoxide. And in this case, cherry red skin is almost always present. And you can see from this that both mechanisms involve respiration. Okay, so this blocks cellular respiration, and this one, let's say, blocks cellular respiration by preventing the arrival of oxygen to tissues. Okay, so you may imagine that those two mechanisms together are synergic in causing toxicity and, of course, asphyxiation and finally death. Hydrogen sulfide is a weak acid. It is used very frequently for the production of sulfur, and sulfur is very important for a lot of chemical and other manufacturing processes. So sulfur is one of the most important chemicals nowadays to be produced all over the world. So you can imagine, since hydrogen sulfide is used for its production, it is also one of the most important chemicals nowadays. But hydrogen sulfide is also present naturally in crude oil, in natural gas in much lower amounts, and in volcanic gases. So it enters the atmosphere also quite often and in big quantities through volcanic eruptions or other kinds of emissions, and hot springs that are just another form of volcanic activity. Hydrogen sulfide is very toxic, even if it is not as famous, let's say, than hydrogen cyanide. It has the same mechanism, but it is more toxic than hydrogen cyanide. But the difference is that hydrogen cyanide has a strong bitter almond smell, so it can be detected, let's say, relatively easily. But hydrogen sulfide has a much stronger smell of rotten eggs. So this is very, let's say, perceivable, and anyone can smell it before it reaches dangerous levels. So as a consequence, poisoning from hydrogen sulfide are not so frequent because you can immediately detect with your nose. Okay. Okay, but in fact, the toxicity mechanism is the same as hydrogen cyanide, so also the death or consequence are mostly the same. Okay, so with this, we have finished gaseous inorganic compounds. We have just two more inorganic compounds that are solid in this case. And the first one is probably one of the most important toxic substances, let's say historically, but unfortunately still a big problem, which is asbestos. Asbestos are technically silicon oxides. Here you can see that we have a lot of different, these are the three most important probably forms of asbestos, and the common part is the presence of silicon oxides. Okay, they can be mixed or bound to different metals, and also with the hydroxide ion to form the different forms of asbestos. But all have in common the final, let's say, macroscopic form. You can see here the white part, which is that of long fibrous crystals. In fact, it is so long and fibrous that you can use it to produce textiles, to produce fabrics. And it has very, let's say, peculiar and very useful characteristics, in particular that it is heat resistant, electricity resistant, any kind of structure involving chemicals. But its heat resistance and heat insulating properties made it important for use, for example, in insulating roof covers in homes and in other buildings, and so on and so forth. So it was very, very important in the past for a lot of different applications, and I mean a lot of non-specialized everyday use. Okay, and you may imagine that it was used for centuries for those purposes. Unfortunately, it's also toxic. Nowadays, in Europe, in particular in the European Union, is totally prohibited. You cannot use it in any way for any application. And in the USA, it is almost totally prohibited. You can use it for some very specific application. And the same is true for many, probably all over the world, but most countries have prohibited asbestos totally or almost totally. As I said, it was used for thermal system insulation, for roof textiles, for firefighters, in particular, also acoustic insulation, and it was used for decorative plaster in homes and other buildings. Frequently used in friction materials, in particular for brakes. You may imagine that all car brakes and clutches, or all train brakes in containing asbestos. And since brakes are consumed over time, okay, you have periodically to change them, to replace them. So you may imagine that all these asbestos in brakes, in clutches, in cars, and in trains has gone into the atmosphere, and it has polluted everywhere. Okay, flooring and roofing, filters, sealants, as I said before, for plumbing and other kinds of tubing. Okay, so all of these materials in particular those friction materials that are subject to, let's say, physiological consume, but everything, in particular roofing materials, is degraded over time, and it releases in the atmosphere lots of asbestos. So you may imagine the huge amount of asbestos that has been released in the atmosphere for centuries. Okay, so it is really, really, let's say, worrying to think about it. The problem with asbestos is exactly the same reason why it was so useful from a technical point of view. Since it is very inert, so it will not burn, it will not conduce electricity, it will not react with anything, okay? So from a technical point of view, it was a very, very good material, and it was very, very resistant. One brand of asbestos in Italy, but I think also abroad, was called Eternit, because they say that it was almost eternal, okay? And in fact, it is true. From a technical point of view, it's a very good and strong material, but the same characteristics make it really dangerous when it comes into contact with living beings. Since it is inert and very, very resistant, it goes into the airways and the lungs, so exposure is mainly through the air, and it arrives to the alveoli and it stays there, okay? Once it arrives in the alveoli, it never goes out. And there it stays, and since it is inert, it will not be degraded in any way by anything. So if you continue being exposed, it will accumulate in the alveoli, and there it will constantly inflammate your tissues in the lungs and alveoli. And when we have inflammation, also we have an immune response, in particular macrophages, destroy this substance. But they will not be able to destroy it because it is so inert that even macrophages cannot destroy it. So those cells will die, and a lot of dying cells with increased inflammation, since they will release all their toxic substances that usually are important to digest, let's say, bacteria and other outside matter. In this case, the cells will die and release the toxic substances into the tissue. So the inflammation caused by asbestos will be increased by the immune response of the body. Okay, so you have accumulation and permanent inflammation, increasing inflammation. So you have a chronic toxicity that develops over time, even 15 or 30 years after you begin being exposed to the material. And of course, since the material is completely inert, it will stay there. Its effect will continue even if you stop exposure. Okay. Unfortunately, one of the most important effects of asbestos is through permanent inflammation, the stimulation of carcinogenesis. And so you may imagine what happens to people, for example, involved in the manufacturing of asbestos in the past. So asbestos are surely carcinogenic, in particular, of course, in the exposure location, which is the lungs, in particular, because a very specific kind of cancer. It's called mesothelioma, and this has been very important in order to obtain payment from manufacturers, since operators in the field developed this kind of mesothelioma that can only be caused by asbestos, and so they can ask to obtain payments from their employers due to exposure to asbestos. Because if you have other kinds of lung cancer, you cannot demonstrate that it is caused by asbestos, even if in fact it is probably caused by them, because asbestos can cause also other kinds of lung cancers. In those cases, much more difficult to obtain payment from employers. Okay. And of course, asbestos are additive or synergic with other causes of lung cancers, in particular with smoking. Okay, so if you were an asbestos operator and you smoked, of course you have much more chances to develop lung cancer. But in addition to carcinogenicity, you also have another kind of specific disease called asbestosis. This is, of course, a chronic and progressive disease, and it progresses without any cure possible. In particular, the fibers cause damage to the lung tissue, and so the production of scars. And we know that scars are not elastic, okay? They are stiff. So the lungs must be elastic in order to expand and contract during respiration. So if you have widespread scarring within the lungs, and of course asbestos causes progressive scarring within the lungs become not elastic. They become plastic. So it will be very hard to expand and contract them. So it will be very hard to breathe. And it is a very specific disease. The symptoms are shortness of breath, crackling sound while inhaling, and coughing, chest pain, and so on. There's no effective treatment, and of course, in time, it causes death due to the fact that you don't manage to breathe anymore. Okay, it's a very worrying effect of asbestos. But probably even worse than what I have told you until now is the history of asbestos, because we know, and let's say the scientific community has known and has said that asbestos are toxic since the end of the 19th century. Okay, so asbestos have been used, even if they are toxic, for, let's say, at least almost 1 century. Okay, and we know, let's say, that the authorities and employers knew that workers suffered from asbestos-related professional disease at least from 1930. Okay, and they, let's say that authority didn't add anything about it, and employers continued to expose workers to this kind of disease like if they didn't know. Okay, and officials also from 1930, and we know from the end of the Second World War that asbestos can also cause not only generic toxicity, but also in particular mesotheliomas. Okay, and yet in the USA they are not completely banned. In the European Union they have been banned only in 1991, mostly or completely in 1999. So from, let's say, at least from 1930 to 1991, it is 60 years of workers being exposed to deadly to fatal contamination of asbestos, and probably a lot of population, not workers, but the general population exposed to probable or dangerous levels of asbestos for at least 60 years, when authorities and employers and the manufacturers knew very well that asbestos are very dangerous, toxic, and at the end also carcinogenic. Okay, this is a very, let's say, worrying trend in all over the history of manufacturing, and in particular of manufacturing involving chemicals. Okay, we have a very good technical substance, so it is used very, very widely, and everyone wants to use it because it is cheap, it is very good from a technical point of view. Okay, then we discover that it is toxic, and nothing happens, nothing does anything until something very strong, or for example a big accident, or pressure from employees, or some manifestation, let's say some protests, public protests happens, and then something will start to happen. Someone will start in the authorities and so on, start to passing laws prohibiting it, and so on and so forth. And this, unfortunately, this is a trend that I don't think it has stopped for good. Okay, but I think asbestos are one of the worst example of this. Okay, so this is everything regarding inorganic toxic compounds. This one. The next topic is next topic is solvent toxicity. Do you have any question on inorganic poison? No? Okay. So let's go on with solvents. Solvents are usually organic compounds that have some, let's say, not special, but specific characteristics. They are mostly liquid, organic, as I said. They have the property of dissolving other organic compounds, and in fact, they are called solvent exactly for this reason. Since they dissolve organic compound, they are mostly lipophilic. We also have hydrophilic organic solvents, but they are few and not widely used. Most of those compounds, since they are organic and lipophilic, are also quite volatile. And all of those characteristics are important for their use, for their technical use, but also for their toxicity. Here you can find some example. I will not go into any detail right now, but it is just to show you that we have a variety of different formulas, different shapes, of different chemical groups. So solvents are a very heterogeneous class. Okay, I speak about them together since they have those properties in common. Okay, but in reality, each one has some individual specific properties that make it different from other ones, and so on. Okay. But this is also to show you that we have really hundreds of different solvents, so it is a huge field. Huh? Okay, so we can use organic solvents for these properties, for the property of being solvents, so for the dissolution of other compounds, for extracting compounds from a matrix. For example, if you want to extract something, some single compounds, important compounds for pharmaceutical use, for example, from natural tissues, from wood, or from the flowers, or from fruit, or from vegetables, use organic solvent for extracting those compounds. They are used for degreasing, for eliminating oils and solid fats from surfaces, for example, for say, for cleaning surfaces. Okay, they are used vice versa in colors, in inks, paints, in order to make them liquid. Most dyes, most pigments are solid powders, for example. So solvents are still used in order to dilute them and make them liquid. And since solvents are usually volatile, they are useful because when you apply those inks or those paints, they will evaporate fast, and the paint or the ink will become blocked on the surface in let's say fast. Okay, so paints will dry almost immediately, and so on. Also for the dilution of substances, and a very important everyday application is dry cleaning. When you get your clothes dry cleaned, an organic solvent, the dry part means that you don't water, okay? And instead of water, you use solvent, organic solvent. So it's not really dry cleaning, it's organic solvent cleaning, okay? But dry in this case has been used to mean without water, okay? But solvents are used not for their solvent properties, but they're used in other ways, okay, not corresponding to their solvent properties, as fuels, so they are burned as fuels, as raw materials to produce other chemicals. They can use as drugs of abuse, as beverage. You may think that it is strange to use a solvent, organic solvent, as beverage, but if you have ever drinked wine, beer, and so on and so forth, all of them, all alcoholic beverages contain a specific organic solvent, which is ethanol, okay? Ethylic acid. Antifreeze agent, they have the properties of lowering the freezing temperature of liquids, so it is useful for this purpose. Explosives, and in the end, after, let's say, the intended use, whatever intended use, they can stay in the environment as pollutants. So this latter is not a real use, but it is more a consequence of all other uses, if not correctly disposed of. Okay. So we have seen that there's a lot of different chemicals that can be used as solvents, but they have some characteristics in common. And those characteristics have consequences. For example, the fact that the fact that they are mostly lipophilic means that just like any other lipophilic compound, they can be very rapidly absorbed from the body by inhalation, especially, of course, most volatile solvents by the skin, the transdermal route, and by ingestion. Of course, ingestion is less common, okay, because they have quite strong smell or taste, so it's not usual to drink organic solvents, apart from some specific kind like ethanol, where ingestion is voluntary, okay, usually. But lipophilicity means very rapid absorption, usually. And this, as we know, is quite dangerous for toxicants. Of course, distribution is also impacted by lipophilicity. So distribution depends on blood amount to the specific organ, and also depends on lipid content, because we know that lipophilic compounds are stored into fat tissue and any fat part of any tissue. Of course, fat tissue are the elective depot or storage tissues for solvents. Transformation is mainly hepatic, so through the liver, and again, we have seen it before, the most important system is the cytochrome P450. In some cases, this system, and in general, hepatic biotransformation, causes the bioactivation to toxic metabolites. Excretion is through the urine, but since they are quite lipophilic, we have to have conjugation before, okay? Glucuronidation, sulfate conjugation, and so on. Also, feces can contain some part of solvent, but as usual, urine is the most important system. And for volatile solvent, also the air. And just like you inhale them, you can exhale them. Okay, so I think we can stop here for now. I hope everything is clear. If not, please ask. And we can stop now, take a break, and come back in 15 minutes, as usual. Okay? Bye. Okay, so let's start again. With solvent toxicity. Now, most organic solvents have some toxicity features in common. Why? Because, as we know, toxicity is related to chemical structure and chemical properties. So, since most solvents have several properties in common, also they share a lot of toxicity properties. For example, since organic solvents are usually lipophilic, they can penetrate the skin in the, sorry, I'm in the screen, right? Okay. Okay. Now it's better, yeah? Okay, so I was saying that most solvents have a strong local skin effect due to the fact that they are lipophilic. So they can penetrate the outer layer of the skin. You remember when we talked about exposition to toxicants, the skin has an outer layer made from dead cells that is mostly lipids. So solvents can penetrate it because they are lipophilic, and also they can dissolve it since they are solvents. Okay, so they will, let's say, destroy that fat layer so that themselves and other toxicants can better penetrate the skin. So there's a double toxicity mechanism toward the skin. And they have an important depressant effect on the central nervous system. So dizziness, and you can lose consciousness up to the death. Why? Because they are lipophilic, up to the point of being able to penetrate the blood-brain barrier. You remember that the brain has the blood-brain barrier that protects it from everything except very lipophilic substances. So they can penetrate the central nervous system and disrupt cell membranes there. Cell membranes, again, are heavily lipophilic, so organic solvent can disrupt them, so they disrupt nervous transmission, nervous signal transmission, and thus depression of central nervous system activity. And for the same reason, they are also neurotoxic. So outside the blood-brain barrier, they can interact with nerves, okay, with neurons and thus nerves, okay, peripheral nervous system. They are usually hepatotoxic. Why? Because the liver is the main organ involved in their biotransformation. So most of them will go to the liver in order to be biotransformed. Not only this, but biotransformation can bioactivate some solvent to toxic metabolites. And so, since this biotransformation happens in the liver, it can also damage the liver. And nephrotoxicity, due to the fact that most of them are eliminated through the urine. So when they are filtered by the kidneys and go to into the urine, toxicity can happen there. Okay. Regarding cancer risk, it is variable. Some solvents are heavily carcinogenic, other much less. So it is more diverse among different solvents. Okay, so we have usually strong hepatic toxicity from solvents. It is called chemical hepatitis. Hepatitis means simply inflammation in the liver. And the most important characteristic is the increase in transaminases. Those are enzymes that should stay within the liver, since they are important for biotransformations happening in the liver. But if you have damage to hepatic cells, the cell will die and release into the blood those enzymes. So you will find those enzymes in high amounts in the blood. This is a sign of liver cell damage. And for the same reason, we can have steatosis or fatty liver. So fat accumulates in the liver, probably because the lipophilic organic solvent will dissolve some fat, and fat will stay there in the liver. And if it continues for a long time, it can become necrosis and or cirrhosis. So diffuse damage will become massive cell death in the liver. And of course, when we reach the stage of cirrhosis, which is extensive death of liver cells, disease is irreversible. Another important fact is that the liver has a limited capacity for biotransformation. So if the liver is working a lot to biotransform the solvents, it will have less, let's say, less time and less enzymes useful to biotransform other things. So high biotransformation of solvents could mean low biotransformation of other compounds, possibly toxic compounds, that are not detoxified by the liver due to the presence of solvents. The main antidote for this kind of compounds is acetylcysteine. This compound, it is a modification of cysteine. This part here is cysteine, and this part is the acetyl, okay? CH3CO is acetyl. And this compound is transformed in the body into glutathione. It's used by the body better to produce glutathione. So administration of acetylcysteine increases glutathione levels within the body. And we know that glutathione is one of the most important detoxifying compounds through phase 2 metabolism in the body. So the antidote to solvent is a generic one because it is just a way, acetylcysteine is just a way to increase the defenses of the body towards generic toxicity, glutathione. Mechanism of hepatotoxicity regards mainly halogenated solvents. They undergo dehalogenation, and this dehalogenation produces free radicals. So if we start from this, for example, is chloroform, very important halogenated solvent. We have that it can be transformed by cytochrome P450 to produce a radical, and this radical can interact with lipids, producing peroxidation. And this is a very important cause of cell membrane instability. Okay, so cell damage, or it can covalent bind to lipids, again damaging their structure. And if you, it can be, let's say, eliminated, the radical, to form another halogenated solvent. So let's say that the cycle can begin again. Instead of CH3Cl3, we have CH2Cl2, but again it can undergo dehalogenation and so on, with the production of radical and so on. But on the other hand, instead of simple dehalogenation with formation of radical, the same enzyme, same CYP enzymes, can produce oxidation. You remember that mono-oxidation is usually carried out by CYP. So we have an hydroxylated form of our solvent, and this form can interact with glutathione, but it can also covalent bind to nucleophiles. Again, here we see that interaction with nucleophiles, it means electron-rich groups. You remember, it is a similar mechanism to the heavy metal toxicity. Amines, carboxylic acids, and thiols in proteins mainly, but also in nucleic acids and even in lipids, can be damaged by this kind of compound. This compound, COCl2, is called phosgene, and it was used during World War I as a nerve gas. So, of course, it's very toxic, okay? Poisonous. And then this compound can undergo conjugation with ion, producing other adducts, hopefully with the toxification. So in this case, you see that you have multiple conjugation with glutathione with the production. Let's say in this case, it's carbon monoxide, which in itself would be poisonous, but those are very, very small amount. So probably it's not dangerous. It is a detoxifying mechanism, or other kinds of detoxifying mechanism, again with the production of not so good molecules. Let's say in this case it's hydrochloric acid. So it is a detoxifying mechanism, but with byproducts that are still a bit dangerous. Okay, but nonetheless, it is better to have this kind of detoxification through glutathione than having the radical mechanism, which is very, very reactive and very, very toxic. Okay, so as a consequence, from what we have seen just now, halogenated hydrocarbons are usually more toxic than non-halogenated solvents, and they are more toxic the more halogen atom they contain. Okay, so for example, carbon tetrachloride, here you can see that it has just one carbon and 4 chlorine atoms. So it will be very toxic. And chloroform has 1 carbon and 3 chlorine atoms. So those are very toxic, just a small organic part and a lot of chlorine atoms. Then you have, as let's say, a bit lower toxicity with those compounds that contain more carbons. Here we have at least 2 carbons, here and here, and 3 chlorine atoms. So it's a bit, let's say that the balance between the organic part and the halogen part is a bit less shifted toward the halogen. Okay, so they are a bit less toxic. And of course, all of these halogenated compounds are more toxic than general non-halogenated hydrocarbons. Okay, regarding this mechanism of toxicity, of course, other solvents, non-halogenated, can have different mechanism of toxicity. But this is a general mechanism for all halogenated compounds, in particular for chlorinated and in part for brominated compounds, solvents in this case. Renal toxicity of solvents can be acute, so for heavy exposure, and it is mainly caused by halogenated hydrocarbons by the same mechanism we have seen before, glycols, toluene, and some petroleum distillates, but it is not very important. General solvents is enough. The main problem with those solvents is glomerulonephritis. It's let's say toxicity that causes the glomerule. The glomerule. It's the basic filtration unit of the kidney, and so as you can understand, if you have inflammation in this part of the kidney, it will not filter anymore. It will let anything pass. So you will lose a lot of important, fundamental substances into the urine. Okay. It seems, for example, that gasoline is a very toxic compound in this regard. Oh, I forgot. Glycols are this kind of compounds where you have two alcoholic function in the molecule: ethylene glycol, propylene glycol, and so on and so forth. Okay, so this is a glycol, but right now it's not really important, just to clarify this part where we have seen that acute exposure is mainly due to halogenated, but also to glycos and so on, while the chronic part, glomerulonephritis, is mostly due to gasoline and related solvents. Okay. Okay. For the central nervous system, we have central neurotoxicity, and this is probably mainly due to a general anesthesia-like activity. I have already told you that this is generally the disruption of nerve membranes that impairs nervous transmission. Okay, so the impairment of neurotransmission is due to disruption of cell membranes due to hypophilicity of solvents. So you can have narcosis or the opposite, euphoria, agitation, ataxia, dysarthria. Dysarthria means difficulty in speaking. Discoordination, of course, since any function of the central nervous system, starting, of course, from the most complicated ones, like speaking, walking, thinking, of course, and going towards the less complicated ones. But also not only the central nervous system, but also the peripheral system. Sorry, this is still central. Since this mechanism, the disruption of membranes, is difficult to demonstrate, it's still not completely understood. But we know, for example, in the past, when a lot of organic solvents were used for paints, we could observe painter's syndrome. And painter's syndrome, of course, was due to the fact that painters inhaled a lot of organic solvents while painting. And it is characterized by depression, retarded psychomotor performance. So what we have just seen before in generic terms, also in decline in memory. But it is practically very similar to this. It's just that it has been, let's say, crystallized into a syndrome because it was typical of a certain kind of profession of worker. This also peripheral neurotoxicity. So we have a neuropathy, so problems in neurotransmission in the periphery, in particular in the movement of extremities, first in the lower and then in the upper limbs. We know that some solvents are surely causing this. For example, normalhexane, methylbutylketone, carbon disulfide are surely involved in peripheral neurotoxicity, and some are suspected of being like styrene and tetrachloroethylene, but the names are not important. So what are the symptoms? We have difficulty in sensing things, so and paresthesia, so a different sensation than what should be caused by the stimulus. Okay, so you cut yourself and you don't feel, for example, pain, but you feel only, let's say, some tingling, something like that. Numbness and loss of reflex or vibration in the limb, and then it progresses with motor weakness. So you don't manage to move the limb properly, or even denervation atrophy. This means that if the nerve stops completely working, the limb will atrophy, since you cannot move it, you cannot use it, and so it atrophies. A particular kind of peripheral neurotoxicity has been studied in detail, and it is toxicity due to hexandione. Hexandione here is a diketone. It contains 2 ketone groups here and here. Of course, it has 6 carbon atoms, so it is an hexane, and dione means 2 ketones. And it was first observed in 1964 in Japan in sandal manufacturing, because workers there used, let's say, not special, but specific kinds of solvents for glue. Again, like in paint, also glues, in order to have fast drying, can be diluted with organic solvents. And in just a few months, those workers could develop symptoms. And 2 solvents, in particular normalhexane and methylbutylketone, here we have already said that they can cause peripheral neurotoxicity. Both of them in the body are biotransformed into this compound 2,5-hexandione. So this is a form of bioactivation. Okay, it is not the solvent itself. For glue, for sandal manufacturing, the workers used the glue containing those solvents, but those solvents were not the cause of toxicity. They were bioactivated within the body to 2,5-hexandione. And this toxicity was mainly due to the axonal death, neuron death, and of course denervation. So the nerve will die, and again this will also cause atrophy. The specific mechanism is the reaction of this compound with proteins, and in particular with lysine amino acid within proteins, which leads to cross-linking. So different proteins will bind together, producing, of course, the loss of function of those proteins. see a lot of toxicity mechanisms involve the disruption of protein function. This underlines the importance of proteins of different kinds, of course, in the functioning of the body in general. Okay. Another important kind of specific toxicity is the toxicity of aliphatic solvents. Aliphatic means that they are unsaturated hydrocarbons, okay, or they contain unsaturated hydrocarbon parts. For example, gasoline, which is a mixture of aliphatic solvents, of aliphatic compounds that are liquid, of course, so they are also solvents, can cause glomerulonephritis and aspiration pneumonia. This means that if you, for any reason, inhale a lot of this volatile liquid, okay, it can cause pneumonia. Nitrates, in particular, can have specific effects since they have a lipophilic part, which is the aliphatic part, but they also include the nitrate part. Here you can see here NO3 minus. This is nitrate group. The nitrate group is a strongly oxidizing group. So here you can see is the small part of hemoglobin. This is called heme. It is written H-E-M-E or H-A-E-M-E according to British or USA English. And as you can see here, you have a very large organic system with fused rings. So this is very, very lipophilic, okay? But it also complexes and includes an iron, okay? And this ion should be and should stay always 2+, okay? So ferrous ion. In this form, heme within hemoglobin has the property of carrying oxygen. So oxygen can bind to iron and be transported to the cells and released to the cells. But those kinds of solvents, of aliphatic nitrates, can interact strongly with heme because they have a lipophilic part that strongly interacts with those fused rings that are lipophilic, and the nitrogen, and in particular the nitric part, the nitrate part, can oxidize iron from 2+ to 3+. So if we have ferric iron here, hemoglobin loses the capacity of carrying oxygen. So again, we will disrupt oxygen transport and cellular respiration, and so we have something like asphyxiation. So the oxidation of iron in hemoglobin is called methemoglobinemia. Okay, where meth means oxidation. So oxidation in the heme part of hemoglobin in blood. Okay, methemoglobinemia. Also, nitrates can penetrate into different tissue due to the lipophilic part, and then they can release just a small part like this or this one, which is nitrogen monoxide, NO. NO is a radical, so it is quite unstable and reactive, but its toxicity is due to, let's say, generic reactivity. It's due to the fact that it is an important signaling compounds within the body. Physiologically, it is used by the body to cause to lower blood pressure, to cause arterial dilation. Yes, dilation. So it means the artery will become larger. Okay, so it will accommodate an higher blood flow, and so pressure will go down. Okay. So this is the physiological role of nitrogen monoxide. But if you intake a lot of aliphatic nitrate, it will produce a lot of arterial dilation, and so a lot of hypotension. And this is, of course, quite dangerous, because heavy hypotension can cause heart arrest. It can cause lower blood afflux in the brain, and so on. And also hepatotoxicity. This is a common, let's say, a common consequence of many solvents intake. Okay, we have seen before what happens with halogenated solvents, in particular here with halogenated aliphatic solvents. Those solvents are relatively widespread, since they can be used for disinfection of water, okay, both in swimming pools, for example, but also for drinking water when in water treatment plants. And so some halogenated solvents can stay within the water when we drink it, or when we go swimming, of course. And we have seen before that we have severe toxicity, in particular for the liver, for the kidneys, but also they can cause problems in the heart, so disruption of heart contraction, so arrhythmias, and also carcinogenicity. Nowadays, carcinogenicity is one of the most important, considered one of the most important parts of halogenated solvent toxicity. In particular, we have three very important solvents that are used in a lot of applications. So 3-chloroethylene, carbon tetrachloride or chloroform, they're very similar, and dichloromethane. Here we have to see in the formulas here, okay, carbon tetrachloride, chloroform, so carbon with 4 chlorides, chlorines, sorry, carbon with 3 chlorines, and 3-chloroethylene. Dichloromethane is again 1 carbon with 2 chlorines. Okay, so 3-chloroethylene is related to the so-called degreaser's flush. Flush means that your skin becomes red, and you feel hot, in particular to the neck and face, and this is called degreaser's flush. You may remember that this kind of solvents are used to degrease, to clean grease and oil from surfaces, in particular in the car industry. So degreasers were people who had the, let's say, the task of cleaning surfaces with solvents. And of course, this is one of the toxic effects. And again, as with asbestos and tobacco drinking, in this case, we have added or potentiated toxicity due to ethanol, because we know that ethanol is heavily toxic to the liver. And so, of course, we had liver toxicity from the halogenated solvent and the liver toxicity from ethanol. And this, of course, potentiates each other. Carbon tetrachloride and chloroform cause severe hepatotoxicity, and dichloromethane or methylene chloride is the same, CH2Cl2, also is metabolized to carbon monoxide. You may remember from before here that some part of the biotransformation path goes to carbon monoxide here. And so also we can have some, usually it's not very important, but we can have some symptoms or some problems related to carbon monoxide. Okay, this is, let's say, the specific toxicology towards living beings, direct toxicity, let's say, okay? But we have a very, very important part related to the environmental toxicology of halogenated aliphatic solvents. This means that toxicity is not directly caused to living beings, but we have changes in the environment that are harmful to living beings. And the most important class in this regard is probably CFCs. CFC means chlorofluorocarbons. The general structure is this, okay? So we have a small organic part, 1 or 2 or 3 maximum carbon atoms, and then all the other atoms are halogens, okay? In this case, chlorine and fluorine, of course, since they are chlorofluorocarbons. But you can see from here that you don't have any hydrogen, okay? So you take an hydrocarbon and you substitute all hydrogens with halogens, okay? And this massive substitution of hydrogen with halogens means that the compounds become very, very stable, very non-reactive. And this was, at the time, very useful because they were used as refrigerants, propellants, and solvents. In particular, for refrigerants, you may remember that, for example, in your freezer or fridge, in air conditioning systems, we need to use particular kinds of solvents that are called, in fact, refrigerants, that can be compressed and they become liquid, or decompressed and they become gaseous. Okay, so they change easily their physical state according to compression or decompression. And CFCs were very good at this task, also because since they are stable or reactive, they didn't risk producing explosions or fires when they were compressed, okay? So this was the reason a lot of CFCs were used in the past as refrigerants and also as propellants in sprays, okay? When you use some spray for, let's say, perfumes or for insecticides and so on, it contains gas, okay, compressed gas that propels, so it pushes out the liquid that is the insecticides or something like that. And also CFCs were very good for this purpose. However, as usually happens, it's a very positive technical characteristic. The characteristic of being stable, so non-reactive, non-inflammable, non-explosive, is also a very bad characteristic for the toxicity from the toxicity point of view. In particular, those compounds damaged the ozone layer in the stratosphere. In fact, those compounds were very stable and they got into the stratosphere because they were not destroyed by anything in the atmosphere. So they were produced at the human level, let's say. They diffused all over the atmosphere. And even in the upper layers of the atmosphere, they stayed there. They were not destroyed by anything, okay? Because they were not very stable. And in the stratosphere, where there's a lot of UV radiation, they will be broken down. We have seen before this kind of reaction with the production from halogenated solvents, okay, with the production of free radicals. And here, of course, we have a lot of halogens that can produce radicals, in particular chlorine radicals. And the chlorine radical can react with ozone in the stratosphere to produce oxygen, so ozone is destroyed. And this compound, something like oxochlorine, is a very reactive compound that reacts another molecule of ozone, regenerating the chlorine radical and oxygen. So, as you can see from here, is a cycle that regenerates chlorine radicals, destroying two ozone molecules. So, as soon as we have the production of this radical, we start a cycle that progressively destroys ozone without stopping, because we have the regeneration of the radical. Okay, so we have massive destruction of ozone, the ozone layer, even in the presence of only small amounts of CFCs. And in fact, this is what really happened when the famous ozone layer hole appeared in the atmosphere. Not only this, but CFCs are also quite strong greenhouse gases. Okay, you may know very well that carbon dioxide is the most important greenhouse gas nowadays due to its production through hydrocarbon burning. But also CFCs were very strong greenhouse gases, stronger than carbon dioxide, but produced in much smaller amounts. And for this reason, mainly for the ozone depletion effect, but also for the greenhouse effect, they have been banned or at least phased out, at least since the 80s in the last century. Okay, so this is the end of the lesson. I hope everything is clear. As usual, if there's any question. In fact, I'm referring to Alessia's question. Okay, she asks if CFCs are mainly damaging to the environment. In fact, they are very stable, and they are not reactive. So they were very good from the safety point of view, so not causing fires or explosions, but also from a toxicological point of view. Since they were much more stable than other halogenated compounds or halogenated solvents, they didn't have the same toxicity. They were much more safer for humans and for animals in general than usual halogenated compounds. However, they are good from this point of view, but very bad from the environmental point of view. Okay? Okay, so I think this is everything for today, unless there's more questions. And okay, so see you next week. Oh, if you have noticed, we usually have our lessons on Thursday and Friday, but next week we will have lesson on Wednesday and Thursday, because on Friday I have a problem. I have the graduation of some of your colleagues, so I cannot give you any lesson. So next Wednesday, again at 12, and Thursday. Okay? So see you next Wednesday. Bye-bye.